I'll begin. Heavenly Father, we thank you for this time we have to meet together and study your creation, and thank you for the rain, and I thank you for these students. Just ask you to bless our time together today, Lord. In your name I pray, Lord Jesus. Amen. So there's a problem in the homework that warrants some discussion because it has a concept that I haven't shared with you, and I don't know, I'm not entirely certain it's in my notes either. I mean, it might be. I don't remember if it's there or not. It might not be there. And this is actually an important idea, especially for the class which follows this, if you guys are taking like differential equations. So in differential equations, if we have a differential equation like this, definition, if you have something like, oh, let me see here. Let's say, I need some letter, say G1, G1, which is a function of x and y, dx, plus G2, which is a function possibly of x and y, dy, equals to 0. This is a differential equation. And, well, I call it the Pfaffian form. Now, you won't see that. You might not see that notation, that language in your differential equations book, but there's a fellow named Pfaff who studied these things in some depth. Anyway, so this kind of differential equation, so let me call this whole expression here omega, just for the sake of not writing that all again. So we say omega is exact on, let's say, D, which is some subset of R2, if there exists some big function, let's say f, such that omega is equal to df. So, in other words, what's df? Well, we have a definition for this, right? This is fx dx plus what? Plus fy dy. Here I'm working in the plane, working in 2 dimensions. So in order for, so what does it mean for a, let's call this thing a differential form, right? It's a form with differentials. What does it mean for this differential form to be exact? What equations have to hold true for this thing to work? See, if you look at this, we would, in my definition, we would need like g1 dx plus g2 dy is equal to fx dx plus fy dy, okay? That's what would have to be true. And so the rules of working with these kinds of things is they're just like, basically just like polynomials. The dx and the dy are independent, all right? So in order for this to hold, we need 2 equations, right? We need, on the one hand, that g1 has to equal fx, right? Which is my notation, of course, for partial f partial x, right? On the other hand, we need g2 is fy, which is partial f partial y, right? This math should look a little bit familiar. It's the same kind of math we did to find a potential function for the vector field in your last homework, right? That one where you had to integrate to find the function whose gradient was the given vector field. We're up against that math again. So if you look at this, there's a theorem that you can see here, right? What happens if you put these 2 things together? What do you got? We know that partial squared f partial y partial x is equal to what? Partial squared f partial x partial y, right? By the commuting of the partial derivatives. So what does this tell us about the g's? So this means that the partial derivative of g1 with respect to y has to equal the partial derivative of g2 with respect to x. See right here? This is a necessary condition. I can't spell necessary. What's wrong with me? Necessary condition for g1 dx plus g2 dy to be equal to df. In order for there to be a function whose total differential matches your differential form, you need this consistency condition on the coefficients of dx and dy. So that's why I made that announcement. My part B, the one I have written in your homework for problem 54, I think it is, if you look at the partial derivatives of the x and the dx and the dy coefficients, you'll see that they don't match. Which means that that form is not exact, which means that you can't actually find, I have in the start of that problem, if possible. Well, the if possible is no for part B, as it's written. That's why in the announcement I said, if you'd like, you can change part B so it kind of matches part A, so that you can actually make sense of the problem more so. Now, so how about, let me be more specific here. Let me show you an example. So let's suppose we're up against something like, I don't know. How about e to the y plus x dx plus, I don't know, x e to the y minus y dy equals to 0. So first question is this an exact form? So let's figure out, is this an exact form? And if it is an exact form, can we find the f, which is the total differential, the f for which the total differential gives you back the differential form, right? And then I'll talk about what it means, if it's possible. Is it possible? I don't know. So this is what? This is my G1 in my current language. This is my G2 in my current language. So what's partial G1 partial y? What's it equal to? Can you guys tell me? E to the y, all right. And what's partial G2 partial x equal to? E to the y? Well, that's good, right? So that means that, in fact, this is in a quote-unquote exact form. And then the theory of calculus then says that you can basically integrate this to find the function whose total differential is these things. Can you guys tell me what it is? I would set f equal to what? How about, to get that, I need an x e to the y, right? To get this, I need a 1/2 x squared, right? If you look at what I've written so far, if we take the partial derivative of this with respect to y, what do we get? We get x e to the y again, right? The partial derivative of this with respect to y, that's 0. So I don't quite match up this term yet. Partial derivative of this with respect to x definitely gives me back here, right? That's how I got this. I integrated the x coefficient with respect to x. Do you recognize this calculation? We've done it a couple times in here. We'll do it more. Don't worry. I try to revisit this calculation about 3 or 4 times this semester. It's an important one. Now let's see here. This, so if I integrate that with respect to y, on the one hand I'd get this, but on the other hand the minus y gives me a what? A minus 1/2 y squared, right? So this right here, right? The total differential of df is exactly the differential equation I started with, right? Now here's the beautiful thing. The solution to star, let me give it a name, I'll make it famous, there we go. Star. Okay, solution to star is simply f of x comma y equals to a constant. So if you can write the exact equation as the differential of a level function, the solutions to that differential equation are simply the level curves of the level function. So in Calculus 2, you guys learned how to solve differential equations, right? How did you do it? You had two methods, right? What were the two methods? Do you guys remember? Use the integrating factor. I wouldn't lead with that, but okay. Math major. Yeah. And separation of variables, right? So those were the two methods. And then this is the third method. This is the method of exact equations. If you can take your differential equation and write it in Pfaffian form like this, and see that the differential equation, the differential form is in fact an exact form, you find the level function for it, you've solved it. Those are the three major methods for solving first order differential equations. But we can't really tell you about the exact equation one in Calculus 2. Why? We think you're not ready for partial derivatives yet, right? Even though we taught you them in Calculus 1, truth be told. But see, so the equation, the solutions to this are x e to the y plus 1/2 x squared minus 1/2 y squared equals to a constant. All right? What would this problem have looked like in your Calculus 2? In the Calculus 2 world, where you study differential equations, how would this problem have come to you? It would have looked like you solve for dy dx. So take star, solve for dy dx. What do you get? So I subtract the dx term to the other side, and then I divide by the coefficient of dy, right? And then divide by the dx. So I'll write down a little bit of that. So I have x e to the y minus y dy equals to minus e to the y plus x, running out of board space here, dx. Solve for dy dx, I get minus parentheses e to the y plus x over x e to the y minus y. That is the differential equation we just solved. How do you like your chances on that with separation of variables or the integrating factor technique? Do you think you can solve that, what I just boxed at the bottom, Calculus 2 style? I don't. Do power series? You monster. Yeah, sure. So my point, guys, is like you have a new tool now. You can solve a whole array of new differential equations you couldn't solve before if you embrace the concept of the total differential. Does it make sense that this has the differential equation star as its differential consequence? Can you see why that's true? What happens? See, there's something we can do to an equation that I've been doing, but I haven't really emphasized. I've just done it, right? I haven't really made a lot of fanfare about this, but there's something new we can do to an equation. We can take its differential, right? When we take a differential of an equation, we get a corresponding equation in terms of differential forms. So when I take the differential of this, I get df, right? I get df equals to, what's the differential of a constant? 0. And what is df equals to 0? That is exactly, by construction, the differential equation we started with. And that is why this level curve is the solution to it. Any questions? So I think, am I right, Ellie? I'm talking about 54? Yeah. Does that make more sense now? You guys were kind of like, what does this problem even mean, right? No? Did you figure it out? You already had it figured out? Kinda? Okay. You're like, what can these words mean, right? Professor Volk is visiting us today. His office is under renovation, so this is the closest, most convenient place you could find to work.
Asbestos everywhere.
Asbestos everywhere? Yeah. They always say asbestos is the bestest, right? Okay, no one ever says that. But anyway, any questions? Yeah.
Just a little bit. I know in the homework, I guess you use parentheses, like partial w, partial x, parentheses, sub y.
Oh, thank you. Thank you. Good question. So your question is like, when in the homework, I have partial w, partial x, parentheses, sub y. And your question is this a second derivative? No, this is not a second derivative. What I mean by this is what I've been writing in class, which is like partial w, partial x sub y, like that. So when I write with the parentheses something, in the context of that, you should understand it's not a differentiation. It is merely me announcing to you that those are the independent variables. So if I write this, what that then entitles me to is the equation partial x partial y equals to 0, and also partial y partial x equals to 0. They are independent variables. That's what's up there. Yeah, it just dawned on me for you guys that we have this subscript partial derivative notation, right? You know, there's another place where there's a danger for confusion there. A lot of times in physics, and sometimes even in here, we'll write a vector, right? We'll write a vector like this, won't we? I mean, I have sometimes. But these are also not partial derivatives typically. That just means x component, y component. You know? It is just a fact of life. We use notations in more than one way, right? So sometimes you just have to figure it out from the context. And there are places where you just don't know. And some of them are really basic. How about this? Only one of these is unambiguous. What is that? Somebody tell me what 3,4 is. You're wrong. It's a 0.34. See what I mean? So you should have picked this one. I should have picked this one. You should have been like, this is the 0.34, because we do not allow interval 4,3. Not usually anyway, except in complex where I do. Because in complex variables, well, actually I put brackets. So like in complex we use this notation. This is the line segment from P to Q. It's kind of a nice notation. Anyway, I digress. Do you guys have questions? If you don't, I'm going to go on to the next thing. Can I erase? A question? No? No? You know what? You know the French do this. Instead of doing, I think I told you guys before, but instead of writing like 3,4, the French will write like this for the interval, so that there's no danger of confusion. Like if you want to include the points, you make the brackets point in. If you want to exclude them, you make them point out. So, yeah. I can't write this, as I said before. I don't want to be thought of as French. So, and also it's just weird notation. Okay, so there's a few more problems in your homework about how to calculate the gradient in other coordinate systems, right? So I should share that with you. So the question is, how do we calculate the gradient in non-Cartesian coordinates? So let's start out with polar coordinates, and I'll try to work this one out for you, okay? So we already know that the gradient in 2 dimensions is what? It's like partial f, partial x, x hat, right? Plus partial f, partial y, y hat. We agree? I mean, that's the definition of the gradient, right? But on the other hand, I have derived for you guys that there is r hat, which is by definition cosine theta, sine theta. And there's also theta hat, and you guys I'll have to check myself on this, minus sine theta, cosine theta, I think. Although, let me take the mystery out of it. Let's just look at a picture, right? If this is r hat, right, and this is theta, where should theta hat point? It should point in the direction of increasing theta. So like it's perpendicular to r hat, it should point like this, okay? So does my formula make sense? If this is cosine theta, right, and this is sine theta, does it make sense? We're going in the negative x direction, the minus sine theta, and up in the cosine theta. Listen, r hat and theta hat, notice r hat and theta hat, both unit vectors, right? And what else do we have? R hat dot theta hat equals to? 0. Very good. So what that means then is we're looking at a pair of orthonormal, that is They're orthogonal and they have length 1 vectors. And if you have a pair of orthonormal vectors in the plane, then you can use those to build any other vector. You see, I can take any vector. This is like a theorem of vector algebra, the part of the course that you guys love the most, right? So theorem, if I have a vector A, I can write it as A dot r hat plus A dot theta hat. Because I can basically look at the part of the vector which is going in the r hat direction, and I can look at the part of the vector which is going in the theta hat direction, and I can build it from these two pieces. Does this make sense? We do the exact same thing with x hat and y hat, right? What is partial f partial x here? You can think of it this way. Partial f partial x is nothing more than the gradient of f, right? Dotted with x hat, because it's the x component. So this is exactly the same idea, but in polar coordinates. Any vector we can build in terms of the so-called polar frame. Okay, so my goal, all right, is to write the gradient of f as equal to, I need to come up with some names for these things. Let's say, you guys, how about Pac-Man? There we go, Pac-Man, r hat, plus Ghost, theta hat, right? So what should the Pac-Man be equal to then? We take the gradient of f, right? And we take the dot product with r hat. That's what that would be, right? Fun fact, Professor Volk took Calculus 3 with me once upon a time. But when he took Calculus 3 with me, it was a 3-hour class, which covered the same topics. Not entirely accurate, actually. The last day of class, I ended classes like, if I recall correctly, I said something along the lines of, next time we're going to blah, 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 blah. And then the students were like, of which Professor Volk was one, were like, this was the last class. And I was like, what? Oh, man. This is the worst. It was the worst experience ever. Like, you thought you have another day to lecture, and it was the end. I don't even remember what I cut out of your course, but you were definitely cheated. You were I think you left it on the final. I put it on the final? That sounds about right. That sounds about right. Was that the semester I hurt my back? No, okay. There was a semester I was lecturing with a hockey stick because I used to be the neighbor of Walt Reichard, who's a hockey guy, and he had like a hockey stick, and I was using it to like prop myself up because I was crooked. I'll tell you what, lecturing with a lower back problem, it's challenging. Okay, so this is exactly, let me write it in the easiest notation. This is fx comma fy, right? Dot product with r hat, which is cosine theta, sine theta, yeah? So you guys can calculate that dot product. What is it? You've got cosine theta, partial f, partial x, plus sine theta, partial f, partial y. But search your heart and realize that this is partial x, partial r, partial f, partial x, plus partial y, partial r, partial f, partial y. And by the chain rule, what is that?
Partial f, partial r.
Very good. That is partial f, partial r. Let's try this same experiment on Ghost. What happens when we take gradient of f dot theta hat? What do we get? We get fx, fy, dot product with apparently minus sine theta, cosine theta, which we could see geometrically this morning. So that gives me a minus sine theta, partial f, partial x, plus cosine theta, partial f, partial y. Now let me just do a little sleight of hand here. This is 1 over r times minus r sine theta partial f partial x plus r cosine theta partial f partial y. Okay? Now that's a little bit of a sneaky trick. I divided and multiplied by r, right? But what is this here? Here you're looking at partial x, partial theta, right? And if you guys don't know where that's coming from, let me remind you, this is all with respect to the polar coordinate formulas, right? X equals r cosine theta, y equals to r sine theta. These equations, from these equations, the partial derivatives flow, right? So this is literally partial x, partial theta. And this over here is, in fact, partial y, partial theta, right? And so what is in the big parentheses? What do we got? Yeah, it's 1 over r times partial f, partial theta. So what have we just shown? We have shown that if we'd like to, we could take the gradient, right? And we can rewrite the gradient in polar coordinates like this. It is in fact partial f, partial r, r hat, plus 1 over r, partial f, partial theta, theta hat. So there you go. That's how we can calculate the gradient in terms of polar coordinates. I know sometimes people want to say, oh, the gradient should just be partial f, partial r, comma, partial f, partial theta, but that's just not how it works out, right? Because the angular coordinate is different than the r coordinate. Like angular coordinates and linear coordinates are different in their nature. So now that we have this formula, we can use it to calculate gradients of all kinds of stuff, right? Let's take this for a spin and see how it works. Any questions before I use it on something? So when would you want to use this formula? The place you'd want to use this formula is if you're working with an application, right, which has some kind of circular symmetry. So all your equations are in polar coordinates, right? The worst thing you could do there would be to switch back to x and y and use the gradient in xy coordinates. Like this is the tool to use in that context. So like here's here's something truly horrible. Example 2, is it? I'll start us out in Cartesian coordinates. Suppose you have f of xy is like equal to inverse tangent of y over x, all right, to the 5th power, there we go, times divided by, oh yeah, this is really horrible, divided by x squared plus y squared to the 3rd power. There, that's a pretty horrible function. Calculate the gradient of this. See, in xy coordinates, I just don't even want to do it, right? But what is this? If you convert to polar coordinates, what am I looking at? What is the formula in polar coordinates? If I convert to polar coordinates, what is this? This is exactly theta, right? Remember, tangent theta is y over x. So let us agree that, let me tell you context here. Context, to make things simple, I'm going to assume x is positive. X being positive means that theta is just straight up inverse tangent of y over x, right? If I don't have that, then we have to quibble over how you define angle and stuff. But anyway, so theta to the power 5. And what's this? R squared, and then it's cubed, right? So r squared cubed is r to the 6th. All right, so let's calculate the gradient of this thing. So we're looking at nabla of theta to the 5th over r to the 6th, right? Which is exactly partial r of theta to the 5th over r to the 6th, r hat, plus 1 over r, partial theta, of theta to the 5th over r to the 6th, theta hat. All right? And then I just have to take these partial derivatives. Of course, we're holding what? Theta and r are independent variables in this context, right? So That's just a what? Minus 6 theta to the 5th over r to the what? 7th, right? R hat. Because the partial derivative of 1 over r to the 6th is minus 6 over r to the 7th, I believe. And this other one, I've got 1 over r, which I won't try to do it that all at once, but the theta derivative is, oh, I guess I can. I'll be lazy. So I can pull the r to the 6th out, right? Because the derivative is with respect to theta, which gives me an r to the what? R to the power 7 in the answer. What's the derivative of theta to the 5th? It's 5 theta to the 4th, right? Times theta hat. And there you go. That is the gradient. I mean, it's still ugly because this is an ugly problem, but don't you think that's a better way to differentiate that than, say, using x, y coordinates? I mean, I think so. Oh no. I thought I was past it. It still sneaks up on me sometimes. How about this? Let's work one in both this Cartesian and polar. So this is a nice one. It's kind of an important one. What if we look at f equals to 1 over the square root of x squared plus y squared? Can you guys tell me how do we differentiate this thing? What's partial f partial x? So I have 1 over the square root, right? So I get what? I get x squared plus y squared to the, what, minus 3/2? And this is the minus half power, right? So minus 1/2 times that times the derivative of the inside function, which gives me 2x. Let me just clean that up a bit. So what we're looking at is minus x over x squared plus y squared to the 3/2, right? What's partial f partial y? By symmetry, right? The same differentiation, x and y appear symmetrically. So we would get minus y over x squared plus y squared, right? To the 3/2. So what's my gradient? My gradient of f is apparently, minus x over x squared plus y squared to the 3/2 minus y over x squared plus y squared to the 3/2. Can you guys tell me how to make that formula prettier? What could I do? I could, there's a common division by that power, right? So I could rewrite this as, just like minus 1 over x squared plus y squared, right? To the 3/2 times the xy vector, right? So that'd be kind of a nice way to leave the answer. So if I was going to do this problem in Cartesian coordinates, that's what it would look like. You can do it, right? You could definitely do it. You guys should be able to do it. But how would this problem look if we use polar coordinates instead? So in polar coordinates, we simply have f equals to 1 over r. And so my gradient of f is simply partial partial r of 1 over r hat, plus 1 over r partial partial theta. I don't really even need to write this because I know that this term is 0 I'm currently writing, right? And so what's the answer? The answer is minus 1 over r squared r hat. That's an important vector field. This vector field, if you had to picture it, it points towards the origin, right? It points towards the origin, and it has an inverse reciprocal dependence in magnitude, right? It drops as the square of the distance from the origin. This is what's known as the Coulomb field, or the gravitational field for like a, a mass. It's attractive, it's always inward pointing, and it decreases as the square of the magnitude from the distance of the center. So this calculation has importance to mathematical physics. Now this over here, if you want to see how this is that, notice that this is also equal to like minus 1 over x squared plus y squared. So that would be r squared, right? And then this is xy. What is xy over the square root of x squared plus y squared? Do you guys see what this is? That is exactly the vector of length 1 that points directly out from the origin. This is r hat in Cartesian coordinates. Okay, I think I made my point. So you guys, I think you should be able to do the homework problems on these, right? Yeah, but I need to talk about the others. Yeah.
Do you always want curvilinear coordinates in r hat and theta hat?
Well, yeah, because yes, please. If the question is to calculate things in terms of r hat and theta hat, please do not use the. I have reserved the Langle-Wrangle, the bracket notation, just for Cartesians. I could imagine another world where you used it for both, but let's not. If I was to do that, I would at least write like Langle, angle, and then like slap a subpolar on it or something, but I try not to do that. If I'm going to make it polar, it's just easier to use these explicitly. And this is what I saw in my physics courses, this notation, all right? Although, okay, full disclaimer, in physics, they always, in spherical coordinates, they flip the meaning of the theta and the phi annoyingly, and also in engineering, so sorry about that. If it's any consolation, there's also a math book which defines the spherical angle totally differently. And I actually kind of like it. If you had to give a name, to the, so in spherical coordinates, right? Let me make myself some space here. So, so you guys know about latitude and longitude, right? No? Yes? Anybody? So which one goes where? If I think of this as the Earth, right? This is a line of constant what? What do you say? Longitude? Is he right? I think these are the longitudes. Constant longitude. That's actually latitude. I can't spell it. Anyway, now in spherical coordinates, how do we go? That's supposed to be a t versus n. So in spherical coordinates for us, we have theta down here, right? And then we sweep phi up from here. And so phi is not really the latitude, is it? One thing you could call it a colatitude, because it's, well, we use co for angles that are complementary. So like the latitude actually would be this angle down here, right? That would be the let me call this thing, I don't know what the name for it. I'm gonna call it alpha. All right. So you could build spherical coordinates where you put your latitude, you actually use latitude, you sweep up from the xy plane, and you let that angle sweep to plus or minus 90 degrees. There's a pretty famous differential geometry book which uses that approach, and it's a nice approach. It makes for good formulas, but we just don't. Like the standard spherical coordinates uses the so-called colatitude, which sweeps from 0 to, all right, somewhere in this desk there is actually a cord to connect my computer. I will find it. Ah, they hid it down here. So, anyway, see, some people will call phi the polar angle because it sweeps off the pole. I try not to do that because I like to think of theta as the polar angle because it's the angle that's with polar coordinates. It's the same that. Now, but that apparently is, there's disagreement on the language here. And I'm probably in the minority. All right, so next up, cylindrical coordinates. How do you calculate the gradient in cylindrical coordinates? This is a short conversation because it's exactly the same. You just add a z-hat term. All right, so cylindrical coordinates gradient formula is the same, right? The spherical coordinates, though, that's actually a little bit more complicated. So spherical coordinates, we can build any vector in terms of the spherical frame by taking dot products with rho hat, phi hat, and theta hat, respectively. And so when I work out that, and we calculated this the other day, right? Rho hat is this, phi hat is that, and theta hat is the same as it was, same as it ever was. I like the way that sounds. Anyway, so you can check that these are perpendicular and they all have length 1. All right? So if I want to figure out how to find the components of a given vector in the spherical frame, I just take dot products. Okay? And when we do those dot products, like gradient of f dot rho hat, which of course gradient is still fx comma fy comma fz in the angle bracket notation, or here's what it looks like in x hat, y hat, z hat. I take the dot product with my rho hat over here, and I get these lovely terms, which if you tilt your head and squint, and you got to remember what the rules of the game here. We have x is equal to rho cosine theta sine phi, right? Y is equal to rho sine theta sine phi. Z is equal to rho cosine phi. These are the spherical coordinate formulas. From the spherical coordinate formulas, all the partial derivatives flow. All right? And so I take this dot product, and you can recognize, oh, that's exactly partial x partial rho. That's partial x partial y partial rho. That's partial z partial rho. So chain rule, guess what happens? We've got just partial f partial rho by essentially the same thing Shane pointed out for the r derivative. And then guess what happens if you take the dot product with the phi hat? Well, it's a little different. You get these things, which then if you really tilt your head and squint, oh, well, we're just missing a rho. See, because if I differentiated x with respect to phi, I'd get cosine theta cosine phi, right? Seems like I've got a minus missing. Wah, wah, wah. Uh-oh. That's no bueno. I wonder, I'm afeared that I have a suspicion that this might be a mistake right here, if I'm not seeing something else wrong. Because I definitely, if I want partial x, partial phi, there's a sign, I'm differentiating sine phi, right? So there's no minus sign to see in partial x, partial phi. So if everything else is right, it means that I've got an error here, and that's supposed to be a minus. Let's see here. The way to check this, guys, we could figure out, well, there's various ways. We could recalculate phi hat, right? How would we do that? We could do it this way. Phi hat is the gradient of phi, divided by the length of the gradient of phi. So how should we, this is actually a good problem for us to have. How would you calculate phi hat? Let me give you a short class in this. So I would say it's the gradient of phi divided by the length of the gradient of phi. Now, should you try to solve for phi and then differentiate it? I would say do not do that. That is a bad way, all right? So instead, what we'll do is we have this wonderful formula. The wonderful formula is z is equal to rho cosine phi, right? And you know what we'll do? We will we'll differentiate that. We'll take the gradient of this, actually. So the gradient of z is equal to the gradient of rho cosine phi. And the way that works is you get the gradient of rho times cosine phi plus rho times minus sine phi gradient of phi. So there's what I'm after. So solve for it. So the gradient of phi is equal to the gradient of z minus the gradient of rho times cosine phi. Now the gradient of z here is just what? 0, 0, 1. And we've got minus cosine phi. What's the gradient of rho? Yeah.
Would you also need to divide by the coefficients of the gradient?
Well, I'm just using the product rule for the gradient here.
Well, like when you solve one, like.
Oh, yes, but yes, thank you. At the moment, I still have minus rho sine phi over here, don't I? Thank you. And then that, if I recall correctly, is just cos theta sine phi, sine theta, sine phi, cos phi. Let's see here. So that gives me like, you know, well, anyway, I don't think I have time to finish this, but we could finish this to check you could continue this and derive the gradient of phi and then normalize it to get phi hat. I'm pretty sure that there's just a typo in the notes right here, okay, guys? And I think I bought into it because down here I've got minuses, and just what the conclusions just are not true unless. So I knew what I needed to get here, right? So I ignored the logical illogic of this step. This step to this step is wrong. It's off by a minus. That means that my phi hat, as claimed up here, is minus phi hat. It's just as simple as that. When we finish that calculation over there, we're going to find that the phi hat is what it should be. Now, anyway, so then you do the same thing with theta hat. And the theta hat's more interesting because it's missing this 1 over rho sine phi term. So also, long story short, the gradient in spherical coordinates is exactly this. This is the gradient in spherical coordinates. The first term is kind of unsurprising. It's just like r hat was for polar coordinates. And this one's a little bit unsurprising. It's kind of like theta hat was for polar coordinates. But what's interesting is that this is the formula for the partial derivative with respect to the theta hat. Now this makes more sense, actually, if you remember in spherical coordinates, right? If this is rho, right, then this distance down here is r. But you see r is equal to rho sine phi. So it's really the same as it was. Like this is r. That is exactly the polar radius. So this is the same as what we just derived in the polar coordinates. But anyway, there's the formula for spherical coordinates, and we'll talk more about what you can do with it tomorrow. But you guys, there's time for questions tomorrow for sure, okay? Like this is pretty much the material that's on the next test, if I recall correctly. Did I tell you the top hat code yet? Uh-oh. Let the record show I have top hatted, and the top hat is 5761. So, and I did mean to hand the attendance sheet out. Did I do that? Well, I'll let you guys go. I know you got.
How accurate is the test that's posted, or how consistent is the test 2 that's posted on supermap.info?
The test.
What's covered here?
The test. The test 2.
Yeah, the test. If you look back in the archives for Calc 3.
Oh man, I have to look.
Yeah.
Where are we looking?
In supermath.
Is it in the multivariate
Calculus.
the archive?
And then it's, yeah, it would be the archive.
Test what? Test 2? Are you asking me test 2 or?
Yeah, solutions for test 2. For a 230.
Are you trying to rickroll me right now? Is that what's happening? No. Oh, is this yours?
It's
Yeah, I feel it.
It's close to that.
Yeah, I'm pretty sure this is yours. Yeah.
it might be about the same as the semester I took.
Yeah, yeah, I think,
I'm just thinking,
yeah,
it looks relatively close to.
yep, yep. Yeah, of course yours, I didn't have 4 tests in your class, so like this has a mixture of the partial differentiation and the integration, but we still have